In the space between stars, where no sun has ever risen, a world moves through the dark. It is a planet, or something very close to what that word has always meant. It has mass and volume, and a surface. Beneath that surface, slow processes continue, but above it, in every direction, there is no star. There is no warmth arriving from outside. There is no light falling at any angle across the ground. What reaches this world instead is something so faint it can barely be called energy at all, a thin, even glow of microwave radiation left over from the earliest moments of the universe, arriving from all directions equally, carrying a temperature of only 2 7/10 of a degree above absolute zero, not warming, not illuminating, simply present, the way the oldest things in the universe tend to be present, quietly, without effect, as a kind of background hum beneath everything that has ever happened since the beginning. This is the defining condition of a rogue planet. Not its mass, not its composition, not the chemistry locked inside it, or the geological processes that may or may not still be running in its interior. What defines it, at the most basic level, is the absence of a star. It belongs to none. It orbits none. It was not captured, and it was not stopped. It moves through interstellar space on its own trajectory, at its own speed, following the slow curve of galactic gravity, rather than the tight pull of any individual sun. The cosmic microwave background is the closest thing it has to external warmth, and at 2.7 Kelvin, warmth is not quite the right word for it. The word planet carries a long history of assumptions. It calls up images of orbits, of a central fire, of the particular dance between a world and the star it attends. Every planet in the solar system moves in relation to the sun. Every moon moves in relation to a planet. Even distant, frozen Pluto, small and tilted and eccentric in its path, still curves around the same star that warms the skin of every living thing on Earth. The relationship between planet and star has been so constant across so many millennia of skywatching that the idea of a planet without one requires a specific kind of attention. It requires a willingness to take a familiar word and press it into unfamiliar territory, to ask whether the thing we are describing is different in kind or only different in circumstance. A rogue planet is a planetary mass object. It falls within a range of masses that begins at the lower end, somewhere around the mass of Earth, perhaps somewhat below, and extends upward through the range of the gas giants, past Neptune, past Uranus, past Saturn, past Jupiter, and continues climbing until it reaches a ceiling. That ceiling sits at approximately 13 times the mass of Jupiter. It is not a perfectly sharp boundary. No line drawn across the continuous spectrum of nature ever is, but it is physically meaningful because above that threshold, something changes. An object massive enough, heavier than about 13 Jupiter masses, can fuse deuterium in its core. It becomes, in the language of astrophysics, something other than a planet. It becomes a brown dwarf. Deuterium is an isotope of hydrogen. In its nucleus, alongside the single proton that defines hydrogen, there sits one neutron. It is common enough in the universe. It was forged in the first few minutes after the beginning, scattered through the hydrogen gas that later became stars and gas clouds and the raw material of everything. And at 13 Jupiter masses, a gravitationally collapsing object reaches the temperature and pressure in its core needed to begin fusing those deuterium nuclei together. Not much, not for long, but enough to place it in a different category, the dim, self-heated class of objects called brown dwarfs, which are neither quite stars nor quite planets, and which generate at least some of their own light, however faint. Below that threshold, no such fusion occurs. Below it, an object simply cools. It may retain heat from its formation for billions of years, glowing faintly in the infrared like an ember gone almost cold, but it produces no energy of its own through nuclear processes. It drifts. At 13 Jupiter masses, an invisible line runs through the dark, not a wall, not a surface, not something that could ever be seen, simply a threshold defined by the physics of nuclear ignition, below which lies the territory of rogue planets, and above which lies the dim self-luminous realm of brown dwarfs. Objects on one side belong to one category, objects on the other side belong to another, and the universe, indifferent to both labels, continues producing objects on both sides in whatever abundance its processes allow. The language used to describe these objects has not settled. Within the scientific literature, the same class of objects appears under several names, depending on which research group is writing and which property they wish to emphasize. Free-floating planet is the term most commonly preferred in peer-reviewed publications, and it is precise in a particular way. It describes what can actually be observed, which is not the object's origin or its history, but its current condition. It floats free. It is unbound. Its motion through space is not governed by the gravity of any star, and its light curve, if it has one, if it is warm enough to be detected at all, does not repeat on the schedule of an orbital period, because there is no orbit. Orphan planet appears in the literature as well, and carries a different weight, a weight that is perhaps more poetic than scientific, implying a world that once belonged somewhere and no longer does. The word orphan suggests a prior attachment, a departure, a loss. It implies formation within a system, with a star as parent, and subsequent separation. There are pathways by which that can happen, but not every rogue planet formed within a system. Some may have condensed in isolation from cold gas in regions far from any star, and never had a parent body at all. For those objects, the word orphan carries a narrative that may not belong to them. Nomad planet appears as a third option, a name that emphasizes perpetual motion, the state of belonging nowhere in particular, of crossing through space on an ancient trajectory with no fixed destination. It is evocative. It is also imprecise in a technical sense, but language, even scientific language, reaches for something when the existing vocabulary does not quite fit. Nomad, orphan, free-floating, three names given to the same cold, wandering class of objects by researchers working at the edge of a category the language of astronomy had not been built to hold. The names are evidence, in a way, that the discovery of these objects arrived before the words to describe them did. Below the lower end of the mass range, there is no sharp boundary, only a gradual thinning of the population and a gradual increase in the difficulty of detection. A body of roughly Earth mass moving through interstellar space would be a rogue planet in every meaningful physical sense. It would have a rocky surface. It might have an interior still warm from the decay of long-lived radioactive isotopes. It might have an atmosphere of some kind, if conditions allowed, but it would be invisible to every telescope currently in operation. The instruments that have found candidates for free-floating planetary mass objects are sensitive to much heavier bodies, gas giant scale, or close to it, and the small, cold, rocky rogues at the lower end of the mass range remain entirely beyond reach. They are predicted to exist. The physics of planet formation and the dynamics of multi-planet systems both suggest that small planets are ejected from their birth systems far more often than large ones. But predicted is not the same as seen. A body twice the mass of Earth, dark and cold, and moving silently through the space between stars, would leave no trace in any current data set. It would be present but undetected, drifting in a darkness that no instrument has yet found a way to penetrate at that scale. The surface of such a world, or of any rogue planet old enough to have radiated most of its formation heat, would receive the cosmic microwave background and essentially nothing else from outside. 2.7 Kelvin, the temperature of the universe itself, averaged across all directions, a faint relic of the time when the cosmos was young enough to be plasma, before it had cooled enough for atoms to form and for light to travel freely. That radiation surrounds everything, every planet, every star, every galaxy, every empty cubic meter of space. But it becomes meaningful only where there is nothing warmer. In the solar system, the sun overwhelms it entirely. On Earth, the sun's radiation heats the surface to an average of roughly 59 degrees Fahrenheit. Even in the outer solar system, at the distance of Pluto, the sun still delivers enough energy to drive a surface temperature tens of degrees above what the cosmic microwave background alone could sustain. On a rogue planet with no star in any direction, that faint background glow is the only external energy the surface receives. It is not enough to warm anything. It is simply the floor, the minimum, the baseline hum of a universe that has been cooling since its beginning and will continue cooling for longer than can be held in the mind. That image, a planetary mass world receiving only the background glow of the universe as its external energy supply, is not a metaphor or an approximation. It is the physical condition of these objects. It is what the equations describe and what the astronomy points toward. And it carries a particular quality of strangeness that is worth sitting with for a moment. Every planet in the solar system exists in a relationship of energy. Earth receives energy from the sun, absorbs some, reflects some, loses some to space. That exchange drives the weather, the ocean currents, the water cycle, the growth of every living thing. Even the most remote and uninhabitable world in the solar system is defined partly by its relationship with the sun's output. A rogue planet has no such relationship. It is not in dialogue with any star. The only external energy it receives is a relic, an afterimage of something that happened billions of years before the planet itself formed. It receives the echo of creation and nothing more. A planet, in the most widely used modern definition, is a body that orbits a star. That condition appears not as a footnote, but as part of the central structure of the definition that most astronomers work with. The 2006 resolution passed by the International Astronomical Union, the organization that serves as the closest thing to a formal authority on the naming and classification of astronomical objects, set out to clarify the status of bodies in the solar system. The resolution famously reclassified Pluto as a dwarf planet, a decision that generated significant public discussion and that continues to be revisited in scientific and cultural contexts. But the resolution also embedded a requirement that has consequences reaching well beyond Pluto. To qualify as a planet under the 2006 definition, a body must orbit the sun, not a star. The sun specifically, and even if the language is read generously, extended by implication to mean any star, the fundamental requirement remains: orbital motion around a stellar body is part of what a planet is. A rogue planet cannot satisfy this requirement. By the formal language of the IAU resolution, a world of 8 Jupiter masses moving through the interstellar medium with a rocky core and a thick hydrogen atmosphere and a magnetic field sustained by convection in a metallic interior is not a planet. It fails the condition of being gravitationally bound to a star. It has no sun to orbit. The IAU itself has not formally adopted a binding definition for rogue planets. The 2006 resolution addressed the solar system. It spoke to the question of what counts as a planet in the neighborhood of the Sun, and it resolved that question by establishing 3 criteria. A planet must orbit the Sun, must have achieved hydrostatic equilibrium, a roughly spherical shape, and must have cleared the neighborhood of its orbit of other material. Rogue planets, by existing outside any solar system, fall outside the scope of the resolution entirely. They are not dwarf planets under the definition. They are not moons. They are not asteroids. They do not fit the category of small solar system bodies, which is the IAU's term for non-planet, non-dwarf planet objects orbiting the Sun. They simply do not appear in the document. The resolution was not written with them in mind, and so they occupy a space outside its reach, unnamed and uncategorized within the framework it established. There is a particular quality to this gap. The International Astronomical Union wrote a definition meant to draw clear lines around what a planet is, and in doing so created a condition, orbital motion around a star, that excludes an entire class of objects that are in every other respect planetary. They form by the same processes. They have the same range of masses. They may have the same internal structures, the same atmospheric compositions, the same geological histories. A planet ejected from its host system 1 billion years after its formation does not change physically in the moment it crosses the boundary into interstellar space. Its interior does not rearrange. Its atmosphere does not transform. Its mass does not shift. Only its orbital relationship, its gravitational bondage to a star, is severed, and under the 2006 resolution, that severance changes its classificatory status entirely, even though nothing about the world itself has changed. This is not a criticism of the IAU, and it was not a failure of the scientists who drafted the resolution. They were addressing a practical problem, the proliferation of Pluto-like objects in the outer solar system, bodies that were accumulating fast enough to make the category of planet unwieldy if Pluto remained inside it. The resolution solved that problem within the domain it was designed to address. The existence of free-floating planetary mass objects in interstellar space was known in 2006, but the resolution was simply not written to include them. Language, like science, addresses the questions it is built to answer, and sometimes a new question reveals the edge of the frame. The objects in question do not know they have not been categorized. A free-floating world of 6 Jupiter masses moving at 40 kilometers per second through the disk of the Milky Way continues moving. Its interior continues whatever slow geological processes its mass and composition permit. Its surface, if it has one in any meaningful sense, sits at a temperature that instruments would measure in Kelvin rather than Fahrenheit, far below the temperature of anything familiar on Earth. And the 7 Kelvin background radiation continues to arrive from all directions, the faintest possible external signal, the universe's own background hum, pressing gently against a surface that has never known sunlight and never will. There is something worth holding here. Not a problem, not a paradox in the technical sense, but a gentle irony at the edge of language and science. The rules written to define what a planet is may formally exclude some of the most planetary things in the universe. Objects formed by the same processes as the planets in the solar system. Objects with the same kinds of interiors and the same range of masses. Objects that, were they still orbiting a star somewhere, would qualify without question. The only difference is the absence of a star, the very quality that makes them extraordinary, the very thing that places them in the dark, moving through the interstellar medium alone and unattached is precisely what the definition cannot accommodate. A planet must orbit a star, but here are worlds that orbit nothing, and the language built to describe the cosmos is still in the process of finding a place for them. That process is slow. Definitions in astronomy do not shift quickly, and the IAU works by deliberation and vote among a large international body of scientists with different research interests and different intuitions about what matters. A formal definition of free-floating planetary mass objects, one that extends the concept of planet to include bodies not gravitationally bound to any star, has not yet been adopted. There are proposals. There are papers arguing for one approach or another. There is ongoing discussion in the community about whether the word planet should be defined by physical characteristics, by mass, by shape, by internal structure, or by orbital condition, by the relationship between a body and the star it circles. Each approach has consequences. Each draws different lines, includes different objects, excludes others. In the meantime, the objects themselves remain what they are. They do not wait for a definition. A world moving through the space between the solar system and the nearest star, perhaps smaller than Jupiter, perhaps larger, perhaps rocky, perhaps gas-rich, perhaps still warm from its formation, tens of millions of years ago, or perhaps cold to the bone across billions of years of isolation, continues its trajectory. It has mass, it has gravity, it may have an atmosphere, it may have weather of a kind, driven entirely by internal heat rather than by the energy of any sun. It may have a magnetic field. It may have a surface where, if an observer could somehow stand upon it and look up, no star would be visible as a disk. Stars would be visible as points of light, as they are from everywhere in the galaxy, scattered across the darkness in all directions. But none of them would be a sun. None of them would rise or set in any cycle tied to the planet's rotation. None of them would warm the ground, only the background, only the ancient, uniform 2.7 Kelvin radiation of the early universe, arriving from all directions in equal measure, pressing against a surface that has never been warmed by anything more specific than the cosmos itself. That is the condition these worlds exist in. That is what they are. And the question of what to call them, whether the word planet fits, whether the word orphan captures something true, whether the word nomad honors their perpetual motion through the dark, is a question that science is still composing an answer to. The answer will come. Language always catches up to the things it discovers, given enough time. New categories form, new definitions are drafted and debated and revised. The history of astronomy is full of objects that required new words, objects whose existence the existing vocabulary had not anticipated, objects for which researchers reached for whatever term seemed closest and then slowly refined it across decades of observation. Pulsars were called LGM, for little green men, by the team that first detected their repeating signal because nothing in the existing catalog suggested what they might be. Quasars were called quasi-stellar radio sources because they looked like stars but behaved like nothing known. The language sorted itself out over time as the objects themselves became better understood. The same process is underway for free-floating, planetary mass objects. The three names, free-floating planet, orphan planet, nomad planet, are early moves in a longer negotiation, a language reaching towards something it does not yet entirely have words for. What the language is reaching toward is this: a class of worlds that are planets in every physical sense, and that formed the same way planets form, that have the same internal architectures as the planets in the solar system, that fall within the same mass range, and that nevertheless move through interstellar space entirely alone, bound to no star, illuminated by no sun, receiving from the universe only the faintest possible background warmth. They are planetary bodies in the dark. The darkness is not incidental to what they are. It is the defining condition of their existence. A rogue planet is not a planet that happens to be far from its star. It is a planet for which the concept of a star, of a home system, of an orbital path, of a year measured in circuits around a central fire, simply does not apply. There is something quiet about that. Not alarming, not troubling, in the way some cosmic revelations can be. Something quieter than that. The feeling of a familiar category gently widening at its edges to include something it had not previously held. The sky, it turns out, contains not only stars and the planets that circle them, it contains worlds that circle nothing, worlds that drift in the spaces between stars, in the dark between the points of light, following the slow gravitational curve of the galaxy itself, rather than the tight and particular gravity of any individual sun. They have been there all along. The instruments that could confirm their presence are recent. The mathematics that predicted their existence in large numbers is more recent still. But the worlds themselves are old, many of them as old as the solar system, or older, moving patiently through a darkness that has never required them to belong anywhere. The precise rules written to define what a planet is, rules composed by careful scientists working in good faith on a real and practical problem, end, at their edge, by not quite reaching these objects. A planet must orbit the sun, or at the very least, must orbit a star. And these worlds orbit neither. They answer to the galaxy, and to nothing smaller. They carry the mass and form of planets, and they carry the condition of permanent, unbroken isolation from any stellar body. They are caught at the edge of the definition, neither quite inside it nor quite outside it, described by 3 different names in the scientific literature and by no formal definition adopted by the body that has authority over such things. That edge is not an empty place. It is where the most interesting questions tend to live, not at the center of a well-established category, where the definitions are confident and the examples are unambiguous, but at the boundary, where the category meets something it did not expect and has to decide what to do about it. Rogue planets live at that boundary. They have always been there. The universe formed them in numbers that may exceed the number of planets in all the solar systems currently known, and placed them in the dark between stars, and left them to move in silence through interstellar space, while the definitions slowly worked their way toward including them. And so they move, in the dark beyond every named and mapped system, in the spaces that no survey has yet fully cataloged. They follow trajectories laid down by gravitational encounters that may have occurred billions of years ago. Their surfaces are cold. Their interiors, in at least some cases, are not. The cosmic microwave background presses against them from all sides, as it presses against everything, as it has since the universe became transparent enough to let it travel freely. 2.7 Kelvin. The oldest warmth in the universe, if warmth is the right word for it. The temperature of the space between everything, arriving at the surface of worlds that belong to nothing and are going in the only sense that applies to objects of this kind, nowhere in particular. The IAU definition sits in its 2006 form. It drew its lines clearly within the solar system. It left the interstellar dark outside its boundary, not by oversight exactly, and not by design, but by the simple fact that it was written to answer one question, and the rogue planets are part of a different question, one the language is still slowly learning to ask. A world of planetary mass, moving through the dark, receiving only the faint background radiation of the early universe as its external energy supply, is either a planet or it is not. The answer depends on which definition is applied, and the definition has not yet been agreed upon. The world itself continues moving, indifferent to the question. Cold, dark, massive, alone, and in a universe full of things that hold still long enough to be named, somehow still ahead of the language that would describe it. In the early life of a solar system, the orbits of young planets do not sit in neat, well-spaced rings. They crowd each other, they shift. Two gas giants can find themselves locked into a kind of gravitational conversation, each one pulling on the other, nudging orbits by small degrees that accumulate over thousands of years into something that cannot hold. The orbital architecture of a newborn planetary system is less a settled arrangement than a slow negotiation, and some negotiations fail. That failure is where the wandering begins. A young system in the first 100 million years of its life is a place of genuine instability. Gas giants, still warm from formation, drift inward and outward as they exchange angular momentum with the disk of gas and dust that lingers around their star. Two of them moving on orbits that edge slowly closer to resonance, the kind of gravitational rhythm in which one planet completes 2 full laps for every one of the others, can begin to tug at each other with growing urgency. The resonance does not hold them steady, it amplifies. Each pass between them transfers a small impulse of energy, and over long cycles of orbit, the impulse accumulates. One planet's orbit stretches outward, the other's falls inward, and eventually, in a single close pass, they come near enough to each other that the exchange is not small at all. That close pass is called a scattering event. It does not look like a collision. The planets do not touch. What happens is subtler and more violent at once, a gravitational slingshot in which one body borrows energy from the other's motion. In the time it takes the two worlds to sweep past each other, the geometry of their orbits is remade. The inner planet may be flung toward its star, arriving in a tight, scorched orbit that it will hold for the rest of the system's life. The outer planet receives the larger share of the exchange, gaining enough velocity to enter an elliptical orbit stretched so wide that its outermost point lies far beyond anything we would call the planetary system. And then, on the long, slow arc of that elongated path, it approaches another world, another scattering, another push. The orbit stretches again. The star's gravity weakens with distance, as all gravity does, and at some point, at some cold and distant position in the darkness beyond the outer planets, the planet's speed exceeds what the star can reclaim. It crosses a threshold with no physical marker. There is no edge in space. The star does not release it consciously, and the planet does not notice the change. What changes is only this: the star's pull is no longer strong enough to curve the planet's path back. The path that was once an orbit becomes a long, straight journey into the dark between stars. The planet is free. It will never return. This is the most common way rogue planets come to exist. Gravitational ejection, the loss of a world through the accumulated violence of close encounters inside its own system, is the mechanism that theoretical models and simulations point toward most consistently. It is not rare. It may be one of the most ordinary fates that can befall a planet in the universe. To picture the timescales involved is to feel how different this process is from anything that fits inside a human life. A single scattering event, the close pass between two planets, unfolds over a period that might range from a single orbital period to a few thousand years. The setup for that encounter, The slow drift of orbits toward resonance and instability takes tens of millions of years. The ejection itself, once the escape velocity of the host star is exceeded, is not instantaneous. It is a gradual release, the star's gravity doing less and less work as the distance grows, the planet's path straightening slowly over centuries as the pull behind it fades to something immeasurable. The moment of true freedom, if it can be called a moment, is not a flash, it is a fading. A gas giant that crosses into interstellar space carries with it everything it had inside the system. Its atmosphere, gathered over millions of years from the protoplanetary disk. Its moons, if any, survived the scattering events that ejected it. Its magnetic field, generated by convection in a vast ocean of metallic hydrogen deep in its interior, still active and humming long after the last light of its host star has faded to a point indistinguishable from any other star. The planet does not know it has been exiled, it simply moves. The systems most prone to ejections are those with multiple gas giants in orbits that cross or converge. The early solar system may have gone through a period of this kind of instability. Models such as the Grand TAC and the NICE model suggest that Jupiter, Saturn, Uranus, and Neptune occupied very different positions in their youth than they do now, and that their interactions reshaped the system profoundly. It is possible, the models suggest, that additional planets once occupied the early solar system and did not survive it. If so, they are out there somewhere in the galaxy, drifting without a star to circle, carrying no record of what they once were part of. The scattering events that produce rogue planets do not favor any particular size of world. A gas giant has more gravitational presence, more mass to throw into the exchange. But a rocky planet, an Earth mass body, or something smaller, is also subject to the forces at work. In a system undergoing chaotic orbital rearrangement, the smaller planets are in some ways more vulnerable. They have less mass to resist being deflected. They carry less momentum into each encounter. A close pass with a gas giant can redirect a rocky planet's orbit dramatically, with what amounts, gravitationally speaking, to very little effort. And rocky planets form in much greater numbers than gas giants. In the dense, warm inner disk of a young planetary system, rocky bodies accumulate by the dozens. Planetesimals building into protoplanets, protoplanets sweeping up debris and merging until a handful of full-sized rocky worlds emerge from the long process of accretion. Many of those worlds survive to become stable planets. Many are absorbed into the larger bodies around them, and some, studies suggest, are thrown clear. Not all at once, and not always in the dramatic scattering events that eject gas giants. A rocky planet can be nudged repeatedly, its orbit shifted slightly by a giant planet passing at a distance, then shifted again, until it finds itself in an orbit that crosses another body's path, leading to a more direct encounter. The process is patient, and it is relentless, and it does not stop until the orbit either stabilizes or fails. N-body simulations, computational models that track the gravitational behavior of many objects simultaneously, each one influencing all the others across time, have explored what happens in young planetary systems over the course of their first 100 million years. The results point consistently in one direction. Small planets, Earth-scale, and super-Earth-scale bodies are ejected far more often than gas giants. In systems where gas giants form and migrate, the rocky inner planets they disturb can number in the dozens, and not all of them survive in orbit. The simulations count the losses. They track the trajectories of ejected worlds as they leave the system's gravitational sphere of influence and enter the wider galaxy. the numbers are large, but ejection from a formed planetary system is not the only path into the dark. In the cold, dense regions of space where stars are born, the molecular clouds that drift through the galaxy like slow rivers of gas and dust, the same gravitational physics that assembles stars can assemble smaller things. A molecular cloud is not uniform. It has structure, filaments, dense cores, pockets of material that collapse under their own gravity, while the larger cloud around them is still dissolving. Most of these cores have enough mass to form a star, and they do, but some are smaller. Some cores contain only enough mass to produce a planetary mass object, a few times larger than Jupiter, or perhaps smaller, and when that object forms, it forms alone. This process is called disk instability in some of its forms, and core fragmentation in others, depending on whether it occurs within a protoplanetary disk that has become gravitationally unstable, or within the larger molecular cloud itself. The distinction matters to theorists. For the object that forms, it matters not at all. What emerges is a planetary mass body that has never been bound to any star, that never occupied an orbit, that was never part of a system. It formed from the same raw material as planets, the same silicates, the same ices, the same mix of hydrogen and heavier elements that built every world in the galaxy. And it formed in the same way planets form, through gravitational collapse and accretion. But it formed where there was no star to bind it, and so from the first moment of its existence, it has been free. There is a quiet strangeness to this. The boundary between a planet formed in isolation and a very low-mass star that failed to ignite is not sharp. The physics of formation overlaps. The physics of composition overlaps. What distinguishes a planetary mass object born in a molecular cloud from a failed star, from a brown dwarf, is primarily mass. Below a certain threshold, roughly 13 times the mass of Jupiter, the object never accumulates enough material and enough internal pressure to ignite even the limited fusion of deuterium that keeps a brown dwarf briefly luminous. It forms. It radiates the heat of its formation for a time, and then it cools and it drifts. For these objects, the word orphan carries a different weight. A planet ejected from a system at least had a star. Once, it was shaped by a star's radiation and a protoplanetary disk's chemistry, and its composition records the conditions of the system it came from. A planet formed in isolation in a molecular cloud had none of that. It was never warm in the way a planet with a sun is warm. It was never lit by anything close. It is not an exile. It is simply a world that formed in darkness and has always been there. Dense stellar environments produce rogue planets through a mechanism distinct from both ejection by internal scattering and formation in isolation. Open clusters, the loose luminous gatherings of young stars that form within the same molecular cloud, are dynamic places in their early history. Stars in a young cluster are packed closely enough that their gravitational fields interact. The cluster as a whole has a collective gravity that shapes the orbits of everything within it, and stars passing near each other, sometimes close enough to be called neighbors by astronomical standards, exert tidal forces on any planetary systems they carry with them. An outer planet, loosely bound to its star by the weak thread of gravity at that distance, is not deeply embedded in the system's architecture. It is the most marginal resident, a passing star, not colliding, not even close by interstellar standards, perhaps approaching no nearer than a small fraction of a light year, can perturb the gravitational field of a planetary system enough to shift an outer planet's orbit. In the tightly bound inner system, a small perturbation produces a small change, and the planet recovers. In the loosely bound outer system, The same perturbation can be enough to push an outer planet onto an orbit from which it cannot easily recover. Several such passes from different directions as the cluster's members move through their collective orbits can accumulate into an instability that ends in ejection. This mechanism operates across the full lifetime of an open cluster, which is itself not long by astronomical standards. Most open clusters disperse within a few 100 million years, their stars drifting apart as the cluster loses its collective gravity through the slow gravitational interference of the galaxy around it. While the cluster is dense, ejection rates are high. As it disperses, the stars move apart and the stellar flyby mechanism weakens. But by then, the early period of intense ejection has already populated the surrounding galaxy with the worlds that were lost. Some of those worlds, ejected with relatively low velocities, may remain loosely bound to the dispersing cluster for a time, not orbiting any single star, but bound to the cluster's collective gravity, drifting slowly outward along trajectories that eventually exceed the cluster's total gravitational pull. They are the last to leave, and when they go, they carry into the open galaxy a velocity that reflects the cluster's own motion through the Milky Way, a memory of the birthplace they are no longer near. It is worth sitting with the range of velocities at which rogue planets travel through interstellar space, not because the numbers are large or surprising, but because velocity is one of the few things about these worlds that is in principle measurable from the outside. A planet ejected by a violent scattering event inside a compact system moves faster than one nudged out slowly by repeated stellar flybys. A planet that formed in isolation within a molecular cloud may have a velocity that reflects the cloud's own internal turbulence at the moment of formation, the same motions that give stars their velocities relative to each other. These are not uniform crowds. They are distributions of worlds moving in all directions at speeds that range across tens of kilometers per second, each following its own ancient line of travel through the space between stars. The path of a rogue planet through the galaxy is not a straight line, though on human timescales it is essentially indistinguishable from one. On timescales of hundreds of millions of years, the galaxy's own gravity, the pull of the galactic disk, the diffuse mass of gas and stars, and dark matter organized into the galactic potential, curves every trajectory slowly. A rogue planet that enters the outer galaxy on a particular heading will, over billions of years, follow a path shaped by the galaxy's mass as a whole. It may pass through stellar neighborhoods, very different from the one it came from. It will never know. The stars it passes are, even at their nearest, far enough away to offer no warmth. The question of how many rogue planets exist in the galaxy begins with the question of how often these processes operate and how many planets they produce per system. For ejection by gravitational scattering, the answer depends on how many gas giants form in a typical system and how chaotic their early orbital evolution becomes. For ejection by stellar flybys, it depends on the density of the stellar environment and the fraction of time a planetary system spends in a dense cluster. For formation in isolation, it depends on how efficiently molecular clouds fragment into planetary mass objects rather than stellar ones. Each of these questions has some observational constraints, and each has significant remaining uncertainty. The 2011 analysis published in Nature by Sumi and colleagues, drawing on a large statistical sample of microlensing events from the optical gravitational lensing experiment survey, found evidence for a substantial population of unbound Jupiter mass objects, perhaps as many as 2 for every main sequence star in the galaxy. Later analyses, working with larger data sets and more refined models, revised that estimate downward. The uncertainty is real and acknowledged, and it means that even the most basic count of rogue planets in the Milky Way remains genuinely open. What the simulations agree on, across many variations of the models, is the direction of the size distribution. Small planets are ejected more often than large ones, not because they are less massive. That is precisely why a rocky planet the mass of Earth, or twice Earth's mass, interacts gravitationally with a gas giant, the way a lighter person interacts with a heavier one. On a seesaw, the momentum transfer favors the smaller body. In a scattering encounter between a gas giant and a rocky world, the rocky world receives a proportionally larger change in velocity. The gas giant barely notices. The rocky world's orbit is remade. This means that for every gas giant moving through interstellar space as a rogue planet, there are predicted to be far more rocky worlds, Earth-sized and smaller, doing the same. The simulations count them by the tens for every gas giant. The observations cannot yet find them. Current microlensing surveys and infrared imaging techniques are sensitive to planetary mass objects at the larger end of the mass range, Jupiter mass and above. Earth mass rogue planets, if they exist in the predicted numbers, are invisible to every instrument humanity has built. Their presence is inferred from theory and from the logic of the ejection mechanism, not from detection. They would be small, cold, and dark. Old rocky worlds without atmospheres, or worlds that once had thin envelopes of gas that slowly leaked away into interstellar space over billions of years. Their surfaces would be frozen. Their interiors might still carry some warmth from the decay of radioactive elements, slow, patient heat that does not light anything but keeps the deep rock from becoming entirely cold. Moving through the galaxy at tens of kilometers per second, passing within a light year of a star every few million years perhaps, never slowing, never stopping, the galaxy would contain them in very large numbers. Not uniformly distributed, they would cluster more densely in the regions where stars are more numerous, where planetary systems formed most often, and cluster dynamics drove the most ejections. The outer galaxy sparsely starred would have fewer. The inner galaxy, dense with old stellar populations and the ancient violent dynamics of the galactic center, might have more. But nowhere across the extent of the Milky Way would they be entirely absent. The scale of this is not easy to hold in mind. It is easier perhaps to think about a single one, a rocky world, perhaps twice Earth's mass, ejected from a young system 4 billion years ago in the early history of the galaxy, when the Milky Way's disk was dense with young stars and planetary systems were forming in large numbers. It left its system moving at something like 20 kilometers per second relative to its host star. Not a violent ejection, but enough. In 4 billion years at that speed, it has crossed thousands of light years. The star it came from is still there, still burning, hosting the planets that survived the event that expelled this one. That star does not know it lost a world. The surviving planets do not know a sibling is gone, and the rogue planet, frozen and dark and moving through the slow turning of the galaxy, carries no record of what it was once part of, only the composition of its rock, the particular mix of silicates and metals that condensed in whatever part of whatever protoplanetary disk first assembled it. A fingerprint in chemistry of a system it left before it was even fully formed. Somewhere in the vast distribution of these wandering worlds, there are rogue planets that have been traveling for longer than Earth has existed. Planets that formed in the earliest generations of star formation, when the galaxy was young and the first systems were establishing themselves. planets that have been free since before the sun condensed from its molecular cloud. They are older than everything in our solar system. They move through a galaxy that has changed enormously around them, the spiral arms shifting, clusters forming and dispersing, stars being born and dying, and through all of it they drift unchanged in their essential condition, dark, cold, and alone. There are also rogue planets that are young. In the stellar nurseries of the present galaxy, in the Orion Nebula cluster, in the young moving groups of stars that share common velocities because they form together, planetary systems are still forming and ejections are still happening. A planet leaving a system today enters interstellar space that is in its local neighborhood, still populated by the dispersing members of the same cluster its host star came from. For a time, it is not entirely alone. The stars around it are still relatively nearby, still crossing its sky over the long arcs of their independent orbits, dimming as the cluster disperses and its members drift apart. Eventually, the cluster dissolves completely into the general stellar field, and the young rogue planet finds itself in the same condition as all the others, surrounded by nothing closer than light years. The process that produces them is old. It began when the first planetary systems formed in the first galaxies. It continues now, and it will continue as long as planetary systems form, which is to say, for a very long time. Every young system carries within it the possibility of an ejection. Every molecular cloud contains the raw material for a planet formed in isolation. Every dense stellar environment puts its outer planets at risk. The universe does not stop making rogue planets. It has been making them steadily for most of its history, and the population of dark wandering worlds that has accumulated over that time is, by the logic of these mechanisms, vast. The smallest of them, the rocky worlds at Earth mass and below, will travel forever without being seen, not invisible in any absolute sense, since in principle sufficiently advanced instruments could detect them, but invisible in practice with every tool that has ever been built or planned. They are the silent majority of the rogue planet population, predicted by every careful simulation of planetary system formation, consistent with every observation that touches on the question, and entirely absent from any catalog of known objects. They are there, moving through the same interstellar medium that carries starlight and cosmic rays and the slow drift of interstellar dust, and they leave no trace that reaches us. The gas giants among the rogue planet population are different only in degree, larger, warmer, carrying more atmosphere and more mass, more detectable by the brief brightening they can produce in a background star's light, but still invisible in any direct sense, still generating no light of their own except the faint infrared glow of their residual formation heat, which cools with time and grows fainter with every billion years that passes. A young gas giant rogue, expelled in the last 50 million years, still glows dimly enough in the infrared to be found by the right survey. An old one expelled 4 billion years ago has cooled to something much harder to see. The oldest are, for practical purposes, as dark as the rocky worlds. What unites all of them, regardless of size or age or composition, is the condition of their travel. They move through space that is, by any measure relevant to a planet, empty. The interstellar medium, the thin gas and dust that fills the space between stars, is not a vacuum in the technical sense, but it is so sparse that a planet moving through it at tens of kilometers per second feels nothing, no friction, no drag, no resistance that would alter its path over any timescale relevant to astronomy. It moves through the medium as if the medium were not there, and in any practical sense for the planet, it is not. The stars the rogue planet passes closest approach once every few million years Perhaps, if the distribution of stellar systems and rogue planets is as dense as models suggest, do not alter its path significantly unless they come very close indeed. They brighten from a point to a slightly brighter point in whatever sky the planet has, and then they dim again, and then they are gone. No warmth reaches the surface, no radiation of consequence. The star passes by, and the rogue planet continues, unchanged. This is the nature of the journey, not dramatic, not marked by events, a steady motion through a space that is almost entirely constant, interrupted by nothing significant on timescales shorter than millions of years, continuing in the same direction with the same speed, on and on across the slow turning of the galaxy. The isolation is not hostile, it is simply complete, and it is permanent for the great majority of rogue planets. A rogue planet can, in principle, be captured by a star. It passes close enough. Gravitational capture requires a three-body interaction or some dissipative mechanism, and the geometry and velocities that allow this are rare. Most rogue planets, once free, remain free. The galaxy will age around them, and they will continue to move through it, cooling, darkening, following the slow curve of the galactic potential across billions of years. No star will rise for them, no orbit will close. The path that opened when they left their system leads outward indefinitely into a dark that will not change. For the small rocky worlds at the lower end of the mass range, the Earth-sized and smaller bodies that simulations predict in the greatest numbers, the journey is the same but smaller in every dimension except duration. They travel through the same interstellar medium, feel the same non-interference, pass the same distant stars. They are colder at their surfaces, with less mass to retain internal heat. They carry less of the radioactive material whose slow decay keeps the deep interior of larger worlds warm for billions of years. They are quieter, they cool faster, and they are, if the simulations are right, vastly more numerous than their larger companions. The galaxy by this picture is not primarily a place of stars. Stars are its bright minority, the visible fraction of a much larger population of bodies that formed the same way planets form and now drift through the same space. Among the planets in orbit around stars, the rocky ones outnumber the gas giants. Among the rogue planets drifting without stars, the rocky ones may outnumber the gas giants by even larger margins. They are the most ordinary products of planetary formation, and the least detectable, the most numerous, and the most invisible. Somewhere in the outer solar neighborhood, not necessarily near, but perhaps within a few light years, moving on a trajectory that will bring it no closer, one of these rocky rogues is passing. It has no name. It has never been observed. Its composition is unknown, though it is almost certainly silicate and metal assembled from the same materials that built every rocky world in the galaxy, because those are the materials that rock planets are made of. It was ejected at some point in the long history of the galaxy, perhaps 4 billion years ago, perhaps 2 billion, perhaps in the youth of some system that is no longer young. It has been traveling since then. It is not warm. Whatever thin atmosphere it may have once carried has likely been lost over the long transit through interstellar space, slowly stripped by the sparse particle radiation that crosses the galaxy from all directions, molecule by molecule, over billions of years. Its surface is exposed to that radiation directly. It is frozen. The temperature at its surface is close to the minimum that the cosmic microwave background radiation, the faint uniform glow that fills all of space as a remnant of the early universe, will allow, at temperature so low that most gases freeze solid and the only things that remain gas are the rarest and lightest. And yet this world is not still. Its interior, insulated from the surface by kilometers of rock, is warmer than the outside by some margin that depends on its composition and how much radioactive material was built into it at formation. The rock there is not frozen. It moves slowly over timescales of millions of years in the patient convective motion that rocky planets sustain as long as they have enough heat from below. There may be no volcanism, there may be nothing that a geologist would recognize as an active process, but the rock moves, and in its moving, it continues the deep, slow life of a planet that has not yet given up all the warmth it was born with. This is the most ordinary story in planetary science, told at the scale the simulations suggest it must be told at. Not the story of one rogue planet, remarkable for some rare property, moving through the dark as an exception. The story of an enormous number of ordinary worlds, most of them rocky, most of them cold, most of them the size of Earth or smaller, each one the straightforward product of the same physical processes that built every planet in every system in the galaxy, ejected in large numbers from young systems because the dynamics of planetary formation are violent enough to regularly throw things clear, formed in smaller numbers in isolation from the fragmenting cores of molecular clouds, drifting now through the interstellar medium in numbers that the simulations count in the hundreds per star, and that the observations have not yet verified, because the observations have not yet been built that can see them. The universe is full of worlds that no star warms, not as an anomaly, not as a rare outcome of exotic physics, but as a predictable, ordinary result of the way planets form and the way gravity works. Every system that forms multiple planets under conditions of orbital instability produces some that it cannot keep. Every dense stellar environment perturbs the edges of the planetary systems within it, loosening the outermost worlds from their tenuous holds. Every molecular cloud that fragments into stellar nurseries also fragments into some objects too small to be stars, assembling themselves in the dark and drifting there. The galaxy makes these worlds steadily, in large numbers as a matter of routine. They are not remarkable objects. They are simply the ones that are hardest to see. And the smallest of them, the Earth mass bodies, the super-Earths, the rocky worlds that the simulations predict should outnumber their gas giant companions by large factors, move through the interstellar medium in what amounts to a vast, silent, and entirely invisible crowd, each one following its own ancient path through the space between the stars, cold and dark and real, present in numbers that the galaxy has been accumulating since the first planetary systems formed, and that will continue to accumulate for as long as planetary systems continue to arise and come apart and send their excess worlds out into the permanent dark between them. A star near the center of the galaxy is doing nothing unusual. It burns steadily, as it has for billions of years, its light spreading outward in all directions through the dense stellar fields of the galactic bulge. An astronomer on Earth points a telescope toward that star and begins to watch. Hours pass, days pass. The star's brightness holds steady, a flat line on a graph, unremarkable. And then, very slowly, the line begins to rise. Something is passing between that star and Earth, not another star, not a nebula. Something dark, something that carries mass but gives off no light of its own, something that will never be seen directly by any instrument yet built. The distant star brightens as the invisible object drifts across the line of sight, its gravity bending the starlight the way a lens bends a beam, drawing the rays together and amplifying what reaches the telescope. The brightening lasts for hours or for a few days, and then just as slowly it fades, the flat line returns, and the dark object continues on its way into the galactic night, unreachable and unnamed. What just passed, bending the light of a star it will never approach, and revealing itself only through that brief and borrowed brightness, was a rogue planet. This is how the dark worlds announce themselves, not by shining, by interrupting the shine of something else. The technique has a name that describes exactly what it is. When mass bends light, any mass, a star, a planet, even a grain of matter dense enough, it acts as a gravitational lens. When that lensing mass moves across the line of sight to a more distant star, the apparent brightness of the background star rises and then falls in a smooth and characteristic curve. The shape of that curve carries information: how massive the lensing object is, how fast it is moving, how it is distributed in space. For most of the history of this technique, astronomers used it to study stellar mass objects, brown dwarfs, the faint ends of stellar populations. Then they looked more carefully at the short events, the brief brightenings that lasted hours rather than years, and they found something unexpected in the statistics. There were too many of them. Short events implied low-mass lensing objects, low-mass, unbound, wandering. The numbers pointed toward a population of planetary mass objects drifting freely through the galaxy, unattached to any star, too cold and dark to detect any other way. The elegance of gravitational microlensing as a detection method lies precisely in what it does not require. The rogue planet does not need to be warm. It does not need to reflect light from a nearby star, because there is no nearby star. It does not need to emit radiation at any wavelength. It needs only to have mass and to pass in front of something bright. The galaxy provides both conditions in abundance: mass, spread across the dark spaces between stars, and background stars, densely packed in the direction of the galactic center, where the stellar density is highest and microlensing events are most frequent. Every time a dark world drifts across a line of sight between Earth and one of those distant stars, the star brightens for a little while, and if someone is watching, the event is recorded. Most of the time, no one is watching that particular star. Most events go unseen, but the surveys watch millions of stars at once, and in their long accumulation of light curves, the dark worlds leave their marks. One of the longest running and most productive of these surveys began in Poland in the early 1990s and has continued ever since. It monitors the dense stellar fields toward the galactic bulge, recording the brightness of millions of stars night after night, year after year, building a patient archive of light curves from which anomalies can be extracted and studied. The project is called the Optical Gravitational Lensing Experiment, and it has produced, over its decades of operation, one of the deepest and most carefully analyzed datasets in observational astronomy. The researchers who work with it are not looking for individual objects so much as they are reading a population, finding in the aggregate of thousands of events the statistical fingerprint of an entire class of unseen worlds. For years, the survey accumulated events. The stellar light curves rose and fell on their characteristic arcs, most of them caused by ordinary stars or brown dwarfs passing across the lines of sight. The timescales of the events encoding the masses of the lensing objects. And among all those events, a subset stood out. They were short, far shorter than what a stellar lens would produce, lasting on the order of a day or less. Too short for a star, too frequent, statistically, for any known sparse population of brown dwarfs. In 2011, an analysis of that dataset was published, led by a researcher named Sumi, and its conclusion was stark. The short duration events implied a population of Jupiter mass free floating objects that appeared to be nearly twice as common as the stars themselves in the galaxy's main disk. 2 Jupiter mass rogues for every star. The number was large enough to require a moment of stillness when reading it. It meant that the spaces between the stars, apparently empty, apparently cold and featureless, were threaded through with an enormous population of dark wandering worlds. The number has since been revised. Later analyses, working with more data and more careful attention to the statistical models, placed the figure lower, closer to 1 Jupiter mass rogue for every 4 stars, roughly a quarter of a star's worth of Jupiter-sized rogues per star on average. Still a large population, still enough to mean that the interstellar medium is far less empty than it appears. And the revised count covers only the Jupiter mass end of the size range, the heaviest rogue planets, the ones whose lensing events are long enough and strong enough to sit clearly in the data. What happens at lower masses, super-Earths, rocky worlds, bodies the size of this planet or smaller, the surveys cannot yet say. The signals from lower mass lenses are shorter and weaker, falling below the detection threshold of instruments not built to find them. The small dark worlds pass unseen, leaving no record, contributing to a population that can only be inferred from models of planetary formation and ejection, not yet counted by any telescope. The statistical work of the optical gravitational lensing experiment and its successors has done something that individual discoveries cannot. It has established that rogue planets are not rare accidents or exotic outliers. They are a component of the galaxy's overall mass distribution. They are part of the inventory. The surveys measure not individual worlds, but populations, and the populations are real, and they are large. Each light curve in the archive represents a dark world that moved through a line of sight at some point in the galaxy's history and left its brief signature in the light of a star it never touched. Read in aggregate, those signatures spell out a cosmos crowded with wanderers. Infrared imaging offers a different window into the rogue planet population, and it comes with a limitation and an advantage that are mirror images of each other. The limitation is time. A rogue planet can only be detected through its own emitted infrared light if it is young enough to still be warm. In the first tens of millions of years after formation, whether by ejection from a young system or by direct collapse in a molecular cloud, a planetary mass object retains enough of its formation energy to glow faintly at infrared wavelengths. The heat is there, leaking slowly from the interior, and the right instrument, pointed in the right direction, can detect it. But as the object ages, as the heat disperses into space and the interior cools, the infrared glow fades. An old rogue planet, one that has been drifting for billions of years, gives off almost no infrared signal that any current facility could isolate. The technique works only on the young ones, the recent wanderers, and only in the regions of the sky where young objects are concentrated. Those regions are the stellar nurseries. The nearest of them, a few hundred light years away, are dense clouds of gas and dust, where stars are forming now, or were forming in the geologically recent past. In these regions, dozens or hundreds of newly formed stellar and substellar objects are packed into a volume of space, small enough to survey systematically, and among them infrared imaging can pick out the ones that sit in the planetary mass range. The Spitzer Space Telescope, operating at wavelengths too long for human eyes to register, accumulated deep images of several of these young star-forming regions during its years of operation. The Wide-Field Infrared Survey Explorer swept larger areas of the sky at similar wavelengths. Both contributed to growing catalogs of free-floating planetary mass candidates, objects too cool to be stars, too dim and too isolated to be orbiting anything, sitting alone in the infrared with temperatures and luminosities that place them in the planetary range. The difficulty always is the boundary. At what mass does a free-floating planetary mass object become a very low-mass brown dwarf? The two categories occupy the same region of infrared color magnitude diagrams. They can form through different processes. One is a runaway planet, one is a collapsed cloud fragment, but they look similar from across a star-forming region, and distinguishing them requires either an accurate age estimate, a precise mass measurement from spectroscopy, or ideally both. The surveys accumulate candidates. The detailed follow-up work, spectrum by spectrum, narrows the list, and some objects survive the scrutiny and remain genuinely planetary mass, genuinely unbound, their infrared glow, the residual warmth of a formation that ended not long ago in astronomical terms. In the year 2012, a specific object entered the literature in a way that would make it among the most carefully studied free-floating planetary mass candidates known. It was found using the Canada-France Brown Dwarf Survey, a program designed specifically to identify cool, low-luminosity objects through their infrared colors. The object carries a designation that reflects its sky position rather than any poetic description of what it is. CFB DSIR 2149-0403. Its spectrum places its temperature well below that of the coolest ordinary stars. Its luminosity, combined with estimates of its age, suggests a mass between 4 and 7 times that of Jupiter, solidly in the planetary range, well below the deuterium burning threshold that separates planets from brown dwarfs. At the time of its discovery, there was some suggestion that it might be loosely associated with a nearby moving group of young stars, which would have helped constrain its age, but subsequent analyses complicated that picture, and the object's precise status, its age, its origin, whether it was ejected or formed in isolation, remains a question held open with care. What is not in question is that it is there, faintly glowing in the infrared, orbiting nothing, cold enough that its atmosphere likely contains water clouds and methane bands, a world of several Jupiter masses drifting through the space not far from this solar system in the scale of the galaxy. The following year brought another object into focus, identified in survey data and studied through follow-up spectroscopy. PSOJ 318 522 sits within a moving group of young stars, known as the Beta Pictoris group. The moving group provides something valuable, a shared age. Stars that form together from the same molecular cloud move through the galaxy together long after the cloud has dispersed. Their similar velocities, a remnant of their common origin. If an object moves with the group and has the same properties as the group's other members, it is likely the same age, in this case roughly 23 million years, young enough to still be warm, young enough that the infrared glow of formation heat remains detectable. PSO J318 522 has a mass estimated at around 6 times Jupiter's. It is not orbiting any of the group's stars. It moves with them but belongs to none of them. A companion to the group in velocity, but in gravitational terms, free. Its temperature sits near 1160 Kelvin. That number placed against the scale of planetary temperatures, familiar from this solar system, is striking. The surface of Venus, the hottest planet here, runs around 730 Kelvin. PSO J318, and here 522 is hotter than that, significantly hotter, and yet it sits in no star's warmth. Its heat is entirely its own, a remnant of the violence of formation, slowly radiating away into the cold of interstellar space. At 1160 Kelvin, its atmosphere carries complex chemistry, clouds of silicate dust, iron droplets, molecules of water vapor, and carbon monoxide at different layers of the atmospheric column. The infrared spectrum carries the signatures of these molecules, each one absorbing specific wavelengths of the world's outgoing radiation and leaving its mark in the data. From a distance of more than 80 light-years, using telescopes on the ground and in orbit, the atmosphere of a world that orbits nothing has been read in detail. What makes PSOJ 318 522 particularly useful to planetary scientists is the comparison it enables. Directly imaged exoplanets, planets photographed in orbit around their host stars, most of them young and warm enough to glow faintly in the infrared, share many of the same atmospheric characteristics. Their spectra show similar molecular absorption features, similar temperature ranges, similar cloud structures, inferred from how the brightness varies across infrared wavelengths. PSOJ 318 522 looks in its spectrum like a cousin of those directly imaged exoplanets. The difference is context. The exoplanets have a star nearby, a gravitational anchor, a heat source supplementing their own. PSOJ 318 522 has none of that. It is what those planets would look like if the star were removed, if the gravity holding them in orbit were dissolved, if they were set free to drift. Studying it tells planetary scientists something about the atmospheres of young gas giants that no amount of staring at the exoplanets themselves could reveal as cleanly. Because around the exoplanets, the star's own light fills the spectrum and complicates the reading. There is a particular quality to the knowledge that comes from these direct infrared detections. The object is not inferred statistically, not extracted from a population of light curves, but seen in the most indirect and technical sense of seen, but seen nonetheless, its photons arriving at a detector after traveling across a vast distance, carrying information about the world they left. The spectrum is a kind of fingerprint, and the fingerprint is legible. It says, this world has water vapor in its upper atmosphere. It says, the clouds are made of silicate grains. It says, the temperature here is this, and the mass is approximately that. A world that belongs to no star has been measured, characterized, understood in some of its most fundamental properties. From a distance, the light crossing it cannot close in a human lifetime. The surveys that found these objects and the analyses that characterize them are built from long patience. A microlensing survey accumulates years of observations before its statistical arguments become robust enough to support population estimates. An infrared imaging program takes deep exposures of the same regions of sky across many observing seasons, building up signal against the noise, waiting for faint objects to separate themselves from the background. The researchers who do this work are not chasing dramatic moments. They are watching and waiting, checking and rechecking, letting the data accumulate until the pattern becomes clear. The light curves pile up in databases. The catalogs of candidates grow. The follow-up spectra are taken one by one, each one a long night at a large telescope, the aperture open to the sky, the detector counting photons from something that has been drifting through the dark for millions or billions of years without anyone to measure it. In the direction of the galactic bulge, where the stellar density is highest and the probability of a lensing event is greatest, the sky holds a density of background stars that from Earth merge into a soft, unresolved glow. Any telescope with sufficient resolution can separate them, and when it does, it finds millions of individual light sources, each one a potential lamp, against which a dark wanderer might briefly cast its gravitational shadow. The geometry of the situation is intricate. The lensing object must pass within a certain small angle of the line of sight between Earth and the background star, and that angle depends on the mass of the lens and the distances involved. For a Jupiter-mass rogue planet at the middle of the galaxy's disk, the relevant angle is tiny, smaller than the angle a human hair subtends at arm's length. But the stellar fields toward the bulge are so dense, and the survey baseline so long, that events occur at a rate that makes statistical analysis possible. Each event is a story told in a single number. The duration of the brightening, which is called the Einstein crossing time. For a stellar mass lens, that time is measured in weeks or months. For a brown dwarf, in days or weeks. For a Jupiter mass rogue planet, in hours to a day. For an Earth mass rogue, in minutes. The histogram of crossing times across a large sample of events therefore encodes the mass distribution of the lensing population, and reading that histogram carefully is reading the hidden population of dark worlds that inhabit the space between the stars. It requires careful accounting for all the other variables, the distribution of lens and source distances, the velocity distributions of different populations, the efficiency of the survey in detecting events of different durations, but the signal is there, embedded in the data, waiting to be extracted with enough observations and enough care. The next major step in this detection program has a name, a design, and a launch date, now in the past. NASA's Nancy Grace Roman Space Telescope, carrying a wide-field infrared camera with a field of view roughly 100 times larger than the Hubble Space Telescope's primary camera, is designed in part to conduct a dedicated survey of the galactic bulge over multiple seasons, accumulating a sample of microlensing events that dwarfs anything previously collected from the ground. The instrument can simultaneously monitor tens of millions of stars. Its sensitivity in the infrared is high enough that the short, faint events produced by Earth mass lensing objects, events that current ground-based surveys miss almost entirely, will fall within its detection threshold. The projected yield runs into the hundreds or thousands of free-floating planet candidates, spanning a range of masses from Jupiter down toward Earth, providing for the first time a statistically robust picture of how the rogue planet population is distributed across the full range of planetary masses. That picture does not yet exist. The current estimate for Jupiter mass rogues, roughly 1 for every 4 stars perhaps, or perhaps more, depending on which analysis one follows, is based on a relatively small number of events by the standards of what the Roman telescope will eventually accumulate. The lower end of the mass distribution, the rocky worlds and super-Earths and ice giants wandering in the dark between the stars, is entirely unconstrained by observation. Theoretical models of planetary formation suggest they should be numerous, ejected from young systems more readily than the heavier gas giants, whose gravity anchors them more firmly in the architecture of developing solar systems. But until the short lensing events from low-mass rogues are measured in quantity, the numbers remain theoretical, the population hidden behind the limitations of current instruments. The Roman telescope will not answer every question. The smallest rogues, below about an Earth mass, will still fall below threshold, but it will map for the first time a wide swath of the mass distribution and place the estimates on a statistical footing that the current data cannot provide. There is something quietly significant about the method that will do this work. The Roman telescope will not photograph rogue planets. It will not image them in the infrared, will not resolve their surfaces, or measure their diameters, or observe their cloud patterns. It will detect them as brief anomalies in the light curves of distant stars, as interruptions, as absences defined by what they briefly do to the light around them. The dark worlds will never be seen, they will only be measured, and yet from those measurements, a census will emerge. How many, of what mass, distributed in what way, across the stellar neighborhood toward the galaxy's center, a population that has been drifting in complete darkness since before this solar system formed, invisible to every instrument yet built, will begin to be counted, not named, not visited, not known in any specific sense, but counted. The shapes of the light curves they leave behind will accumulate in a database, and from that database, the broad outlines of the dark inventory will begin to resolve. The two methods, microlensing and direct infrared imaging, are in a certain sense measuring complementary populations. Microlensing surveys read the statistical distribution of objects across all ages and all distances along lines of sight through the galaxy, but without being able to say anything about any individual object's nature, temperature, or composition. Direct infrared imaging finds specific objects, characterizes them in detail, reads their spectra, and infers their temperatures and masses, but can only do so for the young and relatively warm, and only in the small volumes of space close enough to study with current instruments. Together they build a picture, each method filling gaps the other leaves open. The nearby young free-floating objects found by infrared imaging are the ones that can be characterized in detail, the ones that give planetary scientists a window into what these worlds are actually like. The statistical microlensing results tell those same scientists how common such worlds are across the galaxy as a whole, setting the context for the individual discoveries. CFBD SIR 214900403 exists in that context, so does PSO J318, 522. They are specific objects, individually known, their properties measured and published and discussed. They stand as representatives of a population that extends, unseen and uncounted, across the full depth of the galaxy, objects too old or too small or too distant to detect, moving through the dark on ancient trajectories, their formation heat long since radiated away into the cold of interstellar space. The two that are known because they happen to be young and nearby and in the right part of the sky when the right instruments were looking. The ones that are not known are not fewer in number for being undetected. They are simply waiting, patient in the way that all physical things are patient, for a better instrument or a more favorable alignment or a longer baseline of observation. Between the galactic bulge surveys and the infrared imaging programs, between the statistical and the specific, between the population and the individual, there is a gap that no current technique can bridge. The old rogue planet, close enough to be nearby but cold enough to be invisible, perhaps drifting through the space just beyond the edge of this solar system, or threading the distance to the nearest star, or crossing some expanse of interstellar dark that no telescope has swept at the right wavelength and the right sensitivity. Such a world would not brighten a background star unless its path crossed one exactly. It would not glow in the infrared because its formation heat is long spent. It would be there, planetary in mass and planetary in character, and it would register on nothing. The gap between what the surveys can find and what must be there is itself a kind of measurement, a measure of how much of the rogue planet population remains, for now entirely beyond reach. The surveys continue. Each observing season adds to the archive. New events are recorded, new light curves analyzed, new candidates identified and followed up. Somewhere in a catalog of infrared sources, there may already be a free-floating planetary mass object that no one has yet examined closely, its colors suggesting something cool and isolated, its distance and mass waiting to be extracted from a spectrum not yet taken. And somewhere in the dense stellar fields toward the galactic center, every night the sky is clear and the telescopes are running. A dark, wandering world is briefly amplifying the light of a background star and leaving its crossing time in the data for someone to find and read and add to the count. PSO J318, 5-22, moves through the space not far from the Beta Pictoris group, carrying its 1160 Kelvin heat outward into the galaxy, its silicate clouds cycling through layers of atmosphere that no sunlight has ever touched. The light it emits, infrared, invisible to human eyes, crosses 80 light years and arrives at the detectors of telescopes built to record it. In those detectors, the photons register as a faint signal at specific wavelengths, each wavelength carrying the imprint of a particular molecule in a particular layer of the atmosphere of a world that belongs to no star. Water, carbon monoxide, the spectral gaps where certain wavelengths of its own outgoing light were absorbed before they could leave. The spectrum, read carefully, describes the atmosphere of a free wandering world in more detail than the first astronomers to detect it could have expected, from something so far away and so entirely alone. From across the dark, the world makes itself legible in the only way it can, by what its warmth does to the light passing through its outer layers, a warmth that is, even now, slowly dimming as the last of the formation heat radiates away into the long silence of interstellar space, and the world moves on, cooler each million years, dimming toward the infrared threshold below which no current instrument will be able to find it, carrying its ancient heat into a darkness that will eventually hold it, cold and silent, for longer than the galaxy has yet existed. At 40 Kelvin, the surface of a rogue planet is colder than anything in the inner solar system has ever been, colder than the poles of Mars in the depth of its winter, colder than the shadow side of Mercury, where the rock has never once been touched by light. The temperature is not merely an absence of warmth, it is a condition, a settled state, a stillness that has persisted for so long that the surface itself has become a record of it, layered in frozen gases that have nowhere to go and no season to lift them. And yet, below that surface, something moves. The contrast is the first thing to hold on to. From outside, a rogue planet in the dark looks like nothing, a body emitting so little radiation that even the most sensitive instruments must search patiently to find it, and many never do. But the outside is not the whole story. The outside is simply the cold that has had the longest time to accumulate. Beneath it, deeper than the frost, deeper than the frozen rock, deeper than the first layers of dense compressed stone, there is warmth. It has been there since the planet formed. It has not stopped. That warmth has a source, and the source is not the sun, because there is no sun. It comes from the rock itself. Inside the mantle of a rocky rogue planet, distributed through the silicate minerals the same way iron or calcium is distributed, sit atoms of uranium, thorium, and potassium. They have been there since the planet assembled from the dust and gas of a molecular cloud, billions of years ago. And since that moment of assembly, those atoms have been doing what unstable nuclei do. They have been decaying. Not quickly, not in any way a human lifetime could register, but steadily, and with the release of heat. Each decay is a small event, the rearrangement of a single nucleus, the emission of a particle that travels a fraction of a millimeter through the surrounding rock before its energy is absorbed as thermal motion. One decay produces almost nothing, but when those atoms are counted in the trillions of trillions, distributed through a body the mass of a planet. The total heat output is continuous and substantial, and it has been running without interruption since long before the first living thing opened its first eye on the first world that ever had one. Radium-238 has a half-life of roughly 4.5 billion years. Thorium-232 has a half-life of 14 billion years. Potassium-40 has decayed more quickly, its contribution diminishing over geologic time, but in the early history of a rocky planet, it contributes substantially to the budget. These numbers matter not because they demand memorization, but because of what they imply. A rocky rogue planet, ejected from its system or formed alone in the dark, carries its own heat engine sealed inside it. That engine requires no fuel delivered from outside. It asks for no light, no gravitational tidal flexing from a nearby body, no proximity to a warm stellar atmosphere. It simply runs on the schedule set by nuclear physics for as long as the isotopes last, which is measured not in years or centuries, but in spans of time that dwarf the current age of the universe. In the uppermost mantle, close enough to the surface that the cooling has progressed furthest, the rock is stiff, rigid, moving on timescales so slow that calling it motion seems almost wrong. But further down, where the accumulated heat of radioactive decay has not yet fully escaped, the rock is warm enough to flow. Not as water flows, not as air moves, but as glass would move if you watched it across 1,000,000 years, oozing imperceptibly under its own weight and the pressure of the layers above. This is mantle convection, and on a world far from any star, in a darkness so complete that light from the nearest galaxy arrives as an imperceptibly faint wash rather than illumination, it is still happening. Warm rock rises slowly, and cooler rock sinks, and the pattern turns over on timescales longer than continents persist on Earth. But it turns. The surface above all of this gives no sign. At 40 Kelvin or even colder, on a very old and very isolated world, the landscape is frozen into a stillness that looks from any angle like permanence. There is no wind, because what little atmosphere might once have existed has long since frozen out, settling as thin deposits across the rock. There is no liquid, because at these temperatures, even most gases that could conceivably reach the surface arrive and stay as solids, condensed into coatings of pale frost. Nitrogen, if it is present, lies flat and still. Carbon dioxide, in some thin layer, holds the shape of whatever surface it last settled onto. The sky above, if sky is even a useful word for the open interstellar medium above the surface, contains nothing that glows close enough to cast a shadow. What faint illumination exists comes equally from all directions. The 7 Kelvin glow of the cosmic microwave background, the relic warmth of the universe itself, so evenly distributed that it creates no gradient, no direction, no sense of up or down in the electromagnetic sense. On this surface, there is nothing to tell east from west. Nothing rises in the east, nothing sets, but the stillness is a skin. It is real, and it is cold, and it covers something that has not stopped moving for billions of years. The planet's interior is not the only thing that shapes what happens at those intermediate depths between the deep mantle warmth and the frozen surface. On a world that formed with the right composition, and in a setting that allowed it to hold a certain kind of atmosphere, something more dramatic is possible. The atmosphere itself can become part of the thermal system, not just a skin over the surface, but a pressure vessel, a blanket, a mechanism for holding the heat below against the cold of space above. Consider a rogue planet close to the mass of Earth, formed from a disk rich in hydrogen and helium. In the inner solar system, such a light atmosphere would be stripped away over time by solar ultraviolet radiation, by the energetic wind of charged particles that flows outward from a star. The hydrogen atoms, light and fast at the temperatures near a sun, exceed the planet's escape velocity and drift away into space. But on a rogue planet, far from any star, that driver of atmospheric loss is absent. There is no stellar wind to speak of. The ultraviolet radiation that does reach the planet from distant stars, from the faint glow of the interstellar medium, arrives at levels orders of magnitude below what a rocky inner system planet would endure. The atmosphere is not being pushed away. It is simply sitting there, held by gravity, resting against the surface, and the question becomes, what does it do to the heat? Hydrogen is not an obvious greenhouse gas. The simple molecule absorbs radiation in certain wavelength ranges, but not the broad, efficient absorption of a molecule like carbon dioxide or water vapor. For a long time, the idea that a hydrogen atmosphere could trap meaningful heat seemed unpromising. But the physics of dense atmospheres opens a different mechanism, one that depends not on a single molecule acting alone, but on pairs of molecules acting together. When hydrogen molecules press closely together under high pressure, they collide with one another frequently enough that pairs of them briefly share a kind of collective behavior. In that brief pairing, they absorb infrared radiation at wavelengths that neither molecule alone would absorb. This is called collision-induced absorption, and in an atmosphere several hundred times denser than the air at Earth's sea level, it happens constantly across enormous numbers of molecular pairs, creating an effective greenhouse mechanism from a gas that at low pressure would provide almost none. The thermal radiation trying to escape from the warm surface below is absorbed before it can reach space. The pressure holds it in. The surface temperature, which would otherwise fall toward the temperature of the surrounding interstellar medium, instead sits substantially higher, high enough in the right conditions that liquid water could exist. That last part carries weight, so let it settle without rushing past it. A world with no sun, moving through interstellar space in conditions of near total darkness, could, under the right circumstances, maintain a surface warm enough for liquid water, not because of proximity to a star, not because of tidal heating from a large nearby body, but because of the pressure of its own atmosphere and the physics of hydrogen molecules colliding in the cold. Whether such conditions actually exist on any real rogue planet cannot yet be determined from the observations currently available. The theoretical framework was laid carefully with real physics by researchers who examined what hydrogen-rich atmospheres at high pressure would actually do. The result was a picture that did not violate any known physical law and opened a question that cannot yet be closed. It remains open in the same way that many of the most interesting questions about rogue planets remain open, not as a gap in understanding, but as a space where the physics permits something and the observations have not yet determined whether that something actually occurs. On a world where liquid water is possible, even in the darkness, even under a thick and pressured sky, the question of what lies beneath the surface takes on a different quality, not urgency, but attention. Below the surface of a rogue planet, where the atmospheric blanket has held the deep internal heat against escape, the geological activity sustained by radioactive decay can drive something familiar. Water in contact with warm rock, under pressure, undergoes chemistry. Minerals dissolve and redeposit. Silicates alter. Iron oxidizes and releases hydrogen. These are the same reactions that happen at the hydrothermal vents on the floor of Earth's ocean, in total darkness, kilometers below the surface, far from the light that drives most of the chemistry at the surface above. The chemistry at those vents does not require sunlight. It requires heat and water and rock. On a rogue planet with the right composition and the right thermal history, all three could be present. The water does not need to be at the surface. It could be sealed beneath ice, warmed from below, protected from the cold above by the insulating mass of the frozen crust. Picture a subsurface ocean on a rogue planet, not as a hypothetical, but as a physical possibility that the laws of geochemistry and thermodynamics do not exclude. The ocean is not sunlit. It is not warmed by tides from a nearby moon. It is warmed from below, through the seafloor, by the heat conducted upward from the mantle, where radioactive decay continues its slow, ancient work. The water is under pressure from the ice above it, possibly kilometers thick, pressing down with a weight that raises the freezing point and keeps the water liquid against the cold that would otherwise claim it. At the sea floor, where the water meets the warm rock, minerals dissolve. Hydrothermal activity alters the chemistry of the water, enriching it with reduced compounds, hydrogen sulfide, molecular hydrogen, carbon dioxide in dissolved form. The water is dark, it is pressurized, it is chemically active. It is in contact with warm rock for as long as the rock remains warm, which, given the half-lives involved, is measured in billions of years. The ocean does not move dramatically. There are no currents driven by surface wind, because the surface is sealed under ice and there is no wind in any meaningful sense. There may be convection, warm water rising from the heated floor, cooler water descending from the base of the ice above, driven by the same temperature differences that drive convection in the mantle below. The motion is slow. The chemistry happens at its own pace, above the ice, beyond the frozen surface, through the kilometers of cold and compressed gas and frozen deposits. The interstellar medium continues as it always has, the same vast, dark, thinly scattered collection of atoms it has been since long before this planet formed. None of that reaches the ocean. The ocean is sealed from all of it. It is a place that, in its physical properties, carries none of the markers by which planetary environments are ordinarily recognized. There is no light in it, there is no day, and yet the warmth is real, and the water is liquid, and the chemistry is ongoing. Set that image aside without resolving it entirely, because there is one more internal process worth following to its end. The same convection that moves heat through the mantle, the slow overturning of rock, driven by the temperature gradient between the radioactive interior and the cooling surface, can drive something in the deepest layers that reaches outward in a different direction entirely. Not upward through the rock, outward through space, at the center of a rocky rogue planet, or at the boundary between the rocky mantle and whatever metallic layer lies below it. Pressure and temperature conditions allow iron to remain liquid. Earth's outer core is liquid iron, and its convection, driven by the slow solidification of the inner core below and the heat escaping upward through the mantle above, generates electrical currents in the conducting iron. Those currents generate a magnetic field. The field extends far beyond the surface of the planet into the surrounding space, and it deflects charged particles, cosmic rays, energetic ions from distant supernovae, the slow drift of protons and electrons that permeate interstellar space in all directions at all times. On a rogue planet in the interstellar medium, such a dynamo is not linked to any star. It does not depend on a solar wind for its relevance, though it is worth noting that the cosmic radiation environment of interstellar space is in some ways more demanding than the radiation environment of the inner solar system. A star provides a magnetic bubble, the heliosphere, that deflects the galactic cosmic ray background before it reaches the planets orbiting within. A rogue planet has no heliosphere. It receives the full flux of galactic cosmic radiation without any outer defense. If it has no magnetic field of its own, that radiation penetrates to the surface, and beyond the surface into whatever depth the higher energy particles can reach. A magnetic field generated from within changes this entirely. The field does not require any external driver to maintain itself, provided the convection in the liquid metal interior continues, which it does as long as heat is flowing outward from the deeper layers, which again it does as long as radioactive decay continues producing that heat. The field is self-sustaining in the same sense that the decay is self-sustaining. It does not need to be fed. It operates from the energy stored in the planet since its formation, working through the physics of conducting fluids and electromagnetic induction, maintaining itself against the slow decay that would eventually bring it to stillness when the heat gradients finally flatten out in some distant future measured in billions of years. From the surface of the rogue planet, if it were possible to stand there in the cold and look out into the dark, the magnetic field would be invisible. It would not glow. It would not cast any light across the frozen landscape. It would not warm anything it passed through. It would simply be there, a shape in the electromagnetic fabric of the local space, bending the trajectories of incoming charged particles, steering them around the planet rather than into it. The deflected particles spiral along the field lines, curving away from the surface, and the protected volume beneath the field is from the perspective of the cosmic ray environment, something like a quiet room inside a much noisier building. The building is interstellar space. The noise is the continuous flux of high-energy particles generated by stellar explosions and accelerated across the galaxy over timescales longer than the solar system has existed. Inside the room, the flux is lower, the shielding is real. Whether this matters for anything that might exist in the layers beneath the surface is a question that belongs to a different kind of inquiry. Here it is enough to follow the physics. The dynamo runs, the field exists, the field deflects, the interior is shielded, the process is complete in itself. It does not require any outcome to justify it. It simply happens, as the decay happens, as the convection happens, as the slow movement of warm rock happens in the mantle above the core, all of it part of a single continuous internal activity that the planet has maintained since its formation and will continue to maintain for as long as its composition and physics allow. The surface, meanwhile, gives almost no sign of any of it. Imagine moving across that surface, not walking, because the idea of walking carries too much of the human world with it, but simply moving, a slow transit from one place to another at the scale of the landscape. The ground is not flat. Geology has not stopped because the planet has left its star. Mantle convection, over billions of years, presses upward in some regions and pulls downward in others, deforming the surface slowly, raising ridges and tilting ancient plains. Volcanic activity, not spectacular. Not the dramatic eruption familiar from images of Hawaiian lava meeting the sea, but slow and quiet, pushing material through fissures in the crust, may have occurred at various points in the planet's history, building up low shields of frozen lava, constructing plains of basaltic rock that have since been buried under frost. Tectonic stresses from the movement of the mantle below cause fractures in the crust, long linear features that cross the landscape in the record of movements that happened slowly enough that nothing on a human timescale would have noticed them happening. In the cold, The frost covers everything eventually. Whatever the original surface composition was, silicate rock, basalt, the remnants of ancient impact craters from the early period of the system's formation, the frost settles over time, collecting in the topographic lows, coating the slopes, gradually muting the sharpness of the relief. At 40 Kelvin, even the rock does not behave quite the way terrestrial rock does. At such temperatures, the thermal expansion and contraction that cracks rock on Earth, the freeze-thaw cycles that break down stone on mountain slopes, do not operate the same way. The surface is cold, and it stays cold, and the processes that shape it are driven not by the cycling of temperature through a range, but by the slow work of internal forces coming from below. Across the landscape there is no sound. Sound requires a medium to travel through, and in the near vacuum above the surface, or in the thin frozen layer of gas that might constitute an atmosphere, there is almost nothing to carry it. The place is not merely quiet. It has a quality of silence that is structural rather than accidental, built into its physical state, not the silence of a room where sound is absent, but the silence of a place where the conditions for sound have not existed for longer than there have been ears anywhere in the universe to hear it. The light, what little light there is, arrives from all directions equally. The cosmic microwave background fills every direction of the sky. The faint smear of the galaxy's own glow, too spread and too distant to illuminate anything at the scales that matter to a surface, contributes something. Individual stars, if they are close enough, contribute a photon here and there, arriving with no particular periodicity, producing no coherent illumination, warming nothing by any measurable amount. The surface absorbs these photons the same way it absorbs everything else, without response, without noticeable warming, in a thermal balance that has long since settled into an equilibrium so low that nothing about it changes rapidly. The planet beneath all of this has layers. The deepest layer, the core, or what occupies that position depending on the planet's composition, is the hottest part, and the part furthest from equilibrium with the space outside. If there is liquid metal there, it is slowly convecting, maintaining the dynamo that sends the magnetic field outward through the layers above. If the planet is entirely rocky, with no metallic core of the kind Earth has, the deepest layer is still warmer than the layers above it, still the source from which heat flows outward on the slow timescale of conduction through rock. Above the core, the mantle, warm enough to flow over geological time, carrying heat upward by convection, pressing against the underside of the crust from below with the patient force of a system that has billions of years left to work. The convection cells are not the dramatic, visible rolls one might imagine. They are spread across hundreds of kilometers, turning on timescales of hundreds of millions of years, moving rock that behaves as solid stone on any shorter timescale, but as a slow, thick fluid on the scale at which the planet operates. Above the mantle, the crust, rigid, fractured, the record of everything the interior has done to the surface over the entire history of the planet. Impact craters from the early solar system era, when the planet was still part of a system and the bombardment was heavy. Volcanic features from periods of higher internal heat, now dormant. Tectonic fractures, ridges, tilted planes of rock that were once flat and have since been deformed by the pressure from below. All of it coated, now in the slow accumulation of frost, in the settled deposits of whatever gases the planet ever had that have since frozen out, in the thin dark dust that has drifted inward from the interstellar medium over the long quiet years since the planet left the warmth of any star behind. Above the crust, the atmosphere, if it remains. On a younger rogue planet with sufficient mass an atmosphere of hydrogen might persist, pressing down on the surface at hundreds of times the pressure familiar from standing at sea level on Earth, trapping the internal heat with the collision-induced absorption of paired molecules, holding the surface at temperatures that seem, against the background temperature of space, almost warm. On an older, lower mass world, the atmosphere may be mostly gone, not stripped violently, but lost slowly, molecule by molecule, over billions of years, to the slow thermal escape of the lightest gases and whatever other processes act on a world in interstellar space. What remains of the atmosphere in those cases is thin and cold, and accomplishes little in the way of insulation. The surface temperature drops toward the minimum set by the cosmic microwave background and the planet's own faint thermal emission. 40 Kelvin, 30, perhaps less, on the oldest and least massive worlds. And above the atmosphere, or above whatever the uppermost layer of the planet is, space, the interstellar medium, the same slow drift of atoms, mostly hydrogen, some helium, traces of heavier elements that fills the space between every star in the galaxy. At the number densities of the typical interstellar medium, those atoms are spaced far enough apart that the space between them is closer to a laboratory vacuum than to any gas a human body has ever moved through. The medium is not empty, but it is very close. And through it, steadily, at tens of kilometers per second, faster than anything human technology has ever launched, the planet moves. The trajectory it follows is not circular. It does not close on any point. It does not return to any place it has been before, at least not on timescales, with any relevance to anything that has ever lived. It was set by the planet's formation, or by the scattering event that launched it from a system it once belonged to, and it has been maintained by the simple absence of any force strong enough to alter it substantially. Gravity from distant stars curves it slightly over long timescales. Close approaches to other stellar systems, if and when they occur across the billions of years of the planet's future, might bend it further. But between those encounters, the planet simply moves through the dark, through the thin, cold medium, past the occasional molecular cloud, past the sparse outer halos of stellar systems it will never enter, through regions of the galaxy where stars are closer together, and through regions where they are further apart. The magnetic field moves with it. The field's shape, a roughly dipolar structure with a character similar to Earth's magnetosphere, but operating in the galactic cosmic ray environment rather than in the solar wind, extends out ahead and behind and to the sides. It deflects the incoming particles steadily, the way a rock in a stream deflects the current, not stopping it, not reversing it, but bending it around the obstacle and leaving a quieter region in the wake. The planet passes through regions of varying particle density, and the field responds, compressing slightly in directions of higher flux, expanding in directions of lower pressure, always maintaining its essential function as long as the convection below continues to generate it. Deeper in, the convection continues. The mantle turns slowly. The heat flows outward steadily. The isotopes decay continuously, each nucleus following its own timetable, set by quantum mechanics, indifferent to the darkness outside, indifferent to the absence of a star, indifferent to the enormity of the interstellar space through which the planet is moving. The decay of a uranium nucleus on a rogue planet in the void between stars is identical to the decay of a uranium nucleus in the mantle of the Earth. The physics does not distinguish. The heat produced is the same. The time scale is the same. The isotope does not know it is alone. This is one of the quieter aspects of the picture. The internal activity of a rogue planet is not a pale imitation of what happens inside a solar system planet. It is the same activity following the same laws on the same timescales. The absence of a star removes the stellar input, the sunlight that warms the surface, the radiation that drives surface chemistry, the solar wind that shapes the upper atmosphere. But the stellar input was never what drove the interior. The interior has always run on its own fuel. A rogue planet did not lose its engine when it lost its star. It kept the engine. It only lost the light. At the surface, that distinction does not immediately comfort. The surface is cold. It has been cold for a long time. The frost is deep, and the silence is total, and the darkness extends in every direction, without limit. Nothing rises over the horizon, nothing sets. The temperature fluctuates on timescales, too slow to feel like fluctuation. The very gradual cooling of the interior over billions of years, the equally gradual reduction in radioactive heat output as the long-lived isotopes slowly diminish. On any human timescale, or any biological timescale, the surface conditions are stable to a degree that no surface exposed to the variable output of a star ever quite achieves. There are no seasons, there are no storms. The surface at 40 Kelvin today will be at 40 Kelvin for a span of time, so long that describing it requires thinking about the remaining lifetime of the sun and then extending past it. Below the surface, in the geological warmth, and further below in the slow convective movement of the mantle, and deeper still in the liquid flow of metal that generates the field, there is a kind of life to the planet that the surface does not show. Not biological life, not the movement of organisms, but the physical activity of a world that is still operating its own internal systems, still maintaining its own heat gradients, still generating structure and chemistry and shielding from the small stores of energy it was born with and has been spending very slowly ever since. The magnetic field arcs outward in the cold, curving away from the planet in the shapes that magnetic fields always take. Not symmetrical, because no field in a complex environment is ever perfectly symmetrical, but broadly structured, with regions of higher and lower intensity, with the characteristic form of a dipole, extended and distorted by the pressure of the galactic particle radiation flowing around it. Charged particles approaching from the front of the planet's trajectory are deflected to the sides. Some spiral down along the field lines near the magnetic poles, as they do on Earth, where they produce auroras in the upper atmosphere. On this planet, if there is an atmosphere to receive them, the chemistry of that entry happens in the cold and the dark, without witnesses. The field is not a wall. It does not reflect everything. The highest energy cosmic rays, those accelerated to relativistic speeds by some of the most energetic events in the galaxy, pass through it with almost no deflection, their momentum too great for the field to redirect. But the lower energy particles, the vast majority of the flux in terms of number, are deflected, and the effect on the environments beneath the surface, whatever those environments contain, is real. And then, at the end of the accounting, what remains is this: a world that generates its own heat from nuclear decay, convects that heat through its mantle, potentially maintains liquid water somewhere in the layers between the warm interior and the cold surface, and generates a magnetic field that reaches outward into the interstellar space through which it moves. None of this requires a star. All of it was assembled at the planet's formation and has been operating in one form or another continuously since then. The planet is not inert. It is not a dead rock in the dark. It is a geological system, quiet on its surface and active below, that has been running independently for as long as it has been free. The field extends outward in the dark, invisible and real, curving the trajectories of charged particles in the cold space around the planet, steady and self-maintained, and asking for nothing from outside, a kind of sufficiency that belongs to the planet alone, carried within it since the moment of its formation, persisting in the silence and the cold of interstellar space, as far from any star as a world can be. The number is not quite settled. That is the first thing to hold. The count of rogue planets in the Milky Way remains one of the genuinely open questions in planetary science, a question with real bounds on one side and a soft dissolving edge on the other. When the long survey of stellar light curves toward the galactic center was completed and analyzed, the initial estimate placed the number of Jupiter mass rogue planets at roughly 2 for every star in the galaxy. Later analysis, more conservative and more careful, revised that figure down to something closer to 1 for every 4 stars. Both numbers are large. The distance between them, though, is where the honest uncertainty lives, and within that gap, the full picture of the rogue planet population remains genuinely unresolved. 1 in 4, that is the more careful figure. For every 4 main sequence stars burning quietly in the Milky Way, the revised analysis suggests at least 1 Jupiter mass rogue drifts somewhere in the interstellar dark, bound to nothing, visible to nothing, orbiting nothing. The galaxy holds something on the order of 100 billion such stars. The arithmetic runs forward slowly and arrives at a number too large to feel quickly. Tens of billions of Jupiter mass worlds drifting without stars, and those are only the ones large enough that the current estimates can be grounded in data. Below that mass, the numbers dissolve entirely into theory. Theoretical models of planetary formation and ejection suggest that smaller rogue planets, Earth mass and below, should be ejected from their birth systems far more readily than gas giants. The gas giants, once formed, carry most of the angular momentum of their systems. The smaller worlds are lighter, more easily flung, less gravitationally bound to the star that made them. If those models hold, the count of smaller rogues per star may not be 1 in 4, but something in the hundreds or the thousands per star, 100 billion stars. The multiplication does not simplify into a comfortable image. It opens instead into something vast enough that the numbers stop performing their usual function and become instead a kind of silence. The galaxy then is not mostly stars. It may be mostly dark, between the points of light, between every sun that rises on some planet, and every system where the sky goes deep with warmth at noon. There may be worlds, not planets orbiting anything, but planets in transit, in interminable passage through the space between one star's gravity and the next. Planetary mass objects moving at tens of kilometers per second through a void that offers no resistance, no warmth, no return. A dark population, invisible from any current observatory except in narrow statistical glimpses, whose true size the present science can only bound from above. The rogue planets counted with any confidence are the largest ones. A Jupiter mass body passing in front of a distant star along a precise line of sight bends that starlight in a way that can be measured. The event lasts hours or days, and then the dark world moves on, and the light returns to what it was, and the record of a passing is left in a light curve that no human was watching for in real time, but that patient accumulation preserved. Those events are rare. The alignment must be nearly exact. The background star must be dense field enough to monitor, and the planet must pass at the right moment. That so many events have been found says something about how many dark worlds must cross those lines of sight, but the events found represent only the ones that fell precisely into the geometry of measurement. The others passed unseen. They always will. Below Jupiter mass, the sensitivity of microlensing drops. An Earth mass rogue planet bends light by a far smaller amount over a far shorter time, hours instead of days, a flicker in a stellar light curve that requires monitoring dense in time and precise in calibration. No survey currently operating reaches that sensitivity over a broad enough field to detect Earth mass rogues directly. Their existence in theory is well supported. Their presence in data is absent. They are the dark below the dark, smaller worlds within an already invisible population, predicted in abundance by every well-tested model of planetary physics, and confirmed by exactly nothing yet observed. That gap between what theory expects and what instruments have found is not unusual in planetary science. It is, in many ways, where most of the science lives, but the gap here is unusually wide and unusually populated. The models are not predicting a few more small rogues than the data shows. They are predicting populations orders of magnitude larger, thousands per star across 100 billion stars, a number that, if true, would mean interstellar space is not empty at all, but filled with slow, cold traffic, each vehicle planetary in scale and entirely lightless. The distribution is not uniform. The rogue planets the galaxy contains are not spread evenly across its 100,000 light-year span, like seeds on a flat table. The galactic bulge, the dense, bright, ancient center, holds stars more closely packed than anywhere in the outer disk, and in that density, the rate of planetary ejections is higher, the interactions between young systems more frequent, the gravitational encounters more likely. What the bulge made in its long history, it made in abundance. The microlensing surveys that have produced the best rogue planet statistics point their instruments toward that center precisely because dense stellar fields mean more background stars to lens and more foreground events to catch. The data is biased toward the bulge, not because the bulge is special, but because it is where the geometry of measurement works best. The outer disk where the sun sits, a moderate star in a moderate arm, unremarkable in its position, is less dense, its systems more widely spaced, its ejection history quieter. Rogue planets exist here too, almost certainly, moving through the same general region of the galaxy that the solar system occupies, some of them perhaps within a few light years of the sun right now. Not detectable, not cataloged, simply present as an implication of the physics. And beyond the disk, the halo, old, sparse, nearly starless, holds fewer still, its gravitational history quieter, and its planetary production lower, an outer shell of the galaxy where rogue planets drift with even less company than in the crowded inner regions. The young stellar clusters are different again. In the Orion Nebula cluster, where new stars are still forming, the stellar density is high enough and the systems young enough that gravitational encounters happen quickly and often. A planetary system that forms in a dense cluster faces disturbances from neighboring systems while it is still young, its orbit still settling, its outermost planets still vulnerable. Surveys of such clusters in infrared light have found objects at the planetary mass boundary, not clearly brown dwarfs, not clearly ejected planets, somewhere in the contested territory between drifting slowly outward through the cluster's collective gravity. Some will escape, some will drift back, some are bound loosely enough to the cluster that they move on long irregular paths through its outer reaches, not quite free and not quite held. In NGC 1333, a younger and smaller cluster still embedded in its parent molecular cloud. The same pattern appears. Infrared imaging finds objects at low enough masses to qualify as planetary mass, but the question of whether they formed within planetary systems and were ejected or condensed directly from the collapsing gas with no star ever nearby remains genuinely open. The two pathways leave no clear signature in the spectrum of a cold, dim object, several million years old. Both are plausible. Both may be occurring simultaneously in the same cluster. The true composition of that low-mass population, how many are genuine ejected planets, and how many are planetary mass objects that formed in isolation, is something no current instrument can resolve. That uncertainty does not diminish the objects themselves. Whatever pathway produced a 4-Jupiter mass body drifting slowly through the outer reaches of a young cluster, the object is there, faintly warm, its surface chemistry shaped by its temperature and composition, its interior still radiating the heat of formation, its trajectory carrying it slowly away from the star-forming region that made it and into the wider, quieter galaxy. Whether it was ever inside a planetary system or never belonged to one, its present condition is the same: cold, dark, alone, moving. The same physics that governs planetary formation and ejection in the Milky Way operates in every other galaxy where stars form and planetary systems develop. There is no known reason why the processes that produce rogue planets here should not produce them there, in the large Magellanic Cloud, in Andromeda, in the 10,000 galaxies visible in any small patch of sky. If each of those galaxies hosts a rogue planet population proportional to its stellar count, and if the Milky Way's population is as large as the theoretical models suggest, then the number of rogue planets across the observable universe climbs into territory where ordinary language of counting becomes approximate. A sextillion is 10 to the 21st power. That figure, if the higher-end predictions are close to correct, may undercount the total. No individual rogue planet outside the Milky Way has been detected. None will be, with any instrument currently operating or any instrument being designed. The distances involved are too large, the objects too cold, the lensing geometry too improbable across intergalactic baselines. Their existence beyond the galaxy is inferred from the physics, not seen in the data, and that inference is strong enough that astronomers treat it as near certainty, but it is still inference, still the careful extrapolation of what is known into a domain where the observations simply cannot reach. The extragalactic rogue planets are the furthest edge of the dark population, known to exist, impossible to count, unreachable by any conceivable present means. What the numbers converge on, regardless of which estimate proves closest to right, is a picture of the galaxy in which starless worlds are not exceptional. They are not rare accidents of unusual gravitational configurations. They are the ordinary output of the process by which planetary systems form and evolve. Every planetary system that has ever undergone a major gravitational reorganization, and most do in their first 100 million years, has contributed something to this population. Some contributed a single small rocky world flung out along an eccentric path that opened slowly into the interstellar void. Some contributed several. Some, in their earliest and most chaotic phase, may have contributed a dozen. Across billions of years of galactic history, across hundreds of billions of stars, the accumulation is continuous and large. The solar neighborhood, the region within perhaps a few light years of the sun, is not expected to be dense with rogue planets in the way the galactic bulge is. But it is not expected to be empty either. If the population estimates are near the right order of magnitude, there should be cold, dark planetary mass objects within a light year, perhaps within half a light year, not detectable with any current instrument, not bright enough in infrared to be seen against the background, not large enough to produce a measurable lensing event on any background star in a useful time frame, present nonetheless, drifting through the same general region of space that the solar system occupies, each following its own ancient path at its own velocity, each carrying the remnant heat of a formation that may have happened in an entirely different part of the galaxy, billions of years ago. The velocities involved are not violent. A rogue planet moves through interstellar space at tens of kilometers per second, typically fast by any ordinary standard, slow against the scale of the galaxy. At that speed, crossing from one side of the solar neighborhood to the other takes millions of years. A rogue planet passing within a light year of the Sun would take that long to do so, and its trajectory would carry it onward afterward with no detectable alteration. The Sun's gravity at that distance is too weak to deflect a passing body significantly, too weak to capture it, too weak to do more than leave the faintest mark on its path. The encounter, if it happens, happens in silence and over geological time. There is something in that motion, slow, persistent, undirected, that mirrors the larger condition of these objects. They are not going anywhere in the purposeful sense. They move because they were once part of something that was moving, and the motion was never stopped. A planet formed in a disk around a young star inherits the rotation of the disk and the velocity of the star. When ejected, it carries that motion outward, and the star's gravity slows it slightly as it recedes. But if enough kinetic energy was transferred in the scattering event, it escapes entirely. From that moment, it moves at a constant velocity through space that offers no friction, no resistance, and no waypoints. It will move at that velocity, in that direction, for as long as the galaxy's structure persists, for billions of years, until some future gravitational encounter changes its path, which may not happen in any humanly conceivable time frame. The objects that formed directly from collapsing gas, without ever belonging to a stellar system, have a slightly different history, but a similar present. They formed in isolation, condensed from a cold cloud of gas and dust under their own gravity, and began their independent existence as completed worlds from the first moment. They inherited the motion of the cloud material from which they formed, the turbulent, slow motion of molecular gas drifting through the interstellar medium. That motion became their own, and they have carried it since through whatever changes in the surrounding environment the long history of the galaxy has brought. Both populations, the ejected and the directly formed, now share the same interstellar medium, moving through the same thin soup of gas and dust and magnetic fields and cosmic rays that permeates the space between stars. Their surfaces, cold and mostly frozen, receive the same steady background radiation, the cosmic microwave background at 2.7 Kelvin, uniformly present in every direction, a faint wash of ancient energy that provides no warmth in any practical sense. The interiors of both types continue their own private energy generation, radioactive decay in the rocky ones, slow thermal contraction in the gaseous ones, the long and quiet release of formation energy that began billions of years ago and will continue for billions more. The rocky ones, the Earth mass and super-Earth mass objects predicted to be the most numerous, carry their warmth deepest within themselves. Whatever surface temperature such a world maintains, close to the background minimum, the layers beneath the surface are warmer, and the layers beneath those warmer still. grading inward toward the gentle heat of isotope decay and mantle convection. The world is not dead. It has simply turned its face entirely away from the outside and kept its warmth inside, where the surface cold cannot reach it. A few kilometers down, temperatures may be far above those of the frozen surface. Deeper still, in a world with sufficient mass and the right composition, the temperature crosses the threshold above which water remains liquid, and below the ice, in the pressurized dark, something chemically interesting persists. That liquid water layer, if it exists, and in some rogue planets it almost certainly does, is not still. Water moving over warm rock dissolves minerals. It carries dissolved materials from one place to another. It creates gradients of temperature, of chemistry, of oxidation state. Those gradients are not life. They are not even particularly close to life in any simple sense, but they are the kind of physical and chemical environment in which on other worlds and in other conditions, the first processes precursive to life have operated. The chemistry of hydrothermal environments is not unique to worlds orbiting stars. It requires only water, rock, and heat is the one thing a rogue planet can provide entirely from within, for timescales long enough to matter. That subsurface ocean, sealed beneath kilometers of ice and rock, is not exposed to interstellar space. It does not experience the cosmic rays crossing the void above. It does not receive the hard ultraviolet radiation that would break apart complex molecules at an unshielded surface. It experiences pressure and chemistry and the slow, patient warmth from below, and nothing else. If chemistry of any complexity develops in that environment, it does so slowly, undisturbed, in conditions that have not changed in millions of years and may not change for millions more. The isolation that makes rogue planets hostile from the outside is what protects their interiors from the outside. The magnetic fields some of these worlds generate add another layer of that protection. A rocky rogue planet with a liquid iron core, convecting steadily under the pressure of the mass above it, can maintain a planetary magnetic field of meaningful strength. That field does not care that there is no star nearby. It does not require solar wind to shape it. It is generated entirely by the internal dynamo and extends outward into the surrounding space, deflecting the slow rain of galactic cosmic rays, high-energy particles that cross the interstellar medium from their origin in supernova remnants and other energetic events. Those cosmic rays left undeflected penetrate rock to a modest depth, producing ionizing radiation in the upper layers. A magnetic field reduces that penetration, and below the surface, the ice and rock shield whatever lies beneath from the remainder. The picture that assembles from all of this is not of a dead population. It is of a population that is simply interior, turned inward, self-sustaining, quiet at the surface, and privately warm below. These worlds do not need the galaxy to provide anything to them. They carry everything they need from the moment of formation, and the long physics of radioactive decay and thermal inertia ensures they will carry it for longer than most stars shine. In that sense, they are among the most persistent objects in the galaxy, not the most energetic, not the most complex, but persistent in the patient way of cold, slow, massive things. The galactic disk turns. The sun and its family of planets complete one orbit around the galactic center roughly every 225 million years. In that time, the solar system passes through different regions of the galaxy, different densities of gas and stars, different concentrations of the dark population. The rogue planets do not orbit the galactic center in quite the same way. Their velocities are their own, dispersed by the history of their ejections, carrying them on paths that may be more eccentric or inclined than the disk's rotation. Some cross through the disk from above and below, moving on paths set billions of years ago. Some circle the center in orbits not unlike stellar orbits, keeping to the plane. There is no single description of how they move, because they are not a coordinated population. They are the accumulated result of a billion separate events, each one a planet departing a system at a different time, in a different direction, with a different energy. What they share is the condition afterward, the silence, the darkness, the slow self-sufficiency of a world that has everything it will ever have and moves through space that will never give it anything more. That condition is the same for a world the mass of Jupiter as for one the mass of the Earth. It is the same for a world that formed 3 billion years ago as for one that formed last week. The interstellar medium receives them all without distinction and surrounds them all with the same thin emptiness, the same distant field of stars that provides no warmth, the same background radiation at the boundary of what temperature means. Some of those worlds, moving at their own pace through the solar neighborhood, will cross within the gravitational reach of a stellar system, not the solar system specifically. The probability of any particular rogue approaching any particular star closely is extraordinarily small across a human timescale, but across billions of years, across the full population of rogues and stars in the galaxy, such encounters happen. A rogue planet passing close enough to a star to be gravitationally perturbed will have its path altered, bent, slowed, perhaps captured into a temporary and highly eccentric orbit, perhaps flung to a new velocity. Captures are rare because the energy exchange required is precise, but they are not impossible. Some fraction of rogue planets that enter stellar systems may become bound to them, not quickly, not cleanly, but eventually trading their interstellar freedom for a new orbit around a star that was not the one that made them. If that happens, the world changes. Not immediately. The frozen surface does not thaw overnight when a star appears on the horizon. The warming, if the new orbit is close enough, takes millions of years. The ice sublimates. The atmosphere, if one is retained, thickens. The pressure and composition of the surface air shift slowly towards something new. The world begins to be, in a very different sense, a planetary world, still carrying the memory of its long interstellar passage in its composition and history, but no longer alone, no longer dark, no longer moving through a void that will offer nothing. Whether this happens rarely or occasionally, or not at all in the history of the galaxy, is not known. The probability is small in any given case, and small probabilities across large numbers sometimes still produce very few events. It may be that most rogue planets remain rogues for the remainder of the galaxy's lifetime, and whatever warmth they carry stays sealed within them until the radioactive heat fades and the mantle stills, and the core slowly solidifies in the cold of a universe that has itself grown old. That end, the gradual cooling, the slowing of convection, the eventual stilling of the iron core, takes longer for larger planets and arrives sooner for smaller ones. A rocky world the size of Earth, moving through interstellar space, will sustain its internal heat for billions of years. Eventually, the longest-lived radioactive isotopes, uranium-238 and thorium-232, with half-lives measured in billions of years, will have decayed enough that the heat production slows below the rate of loss through the surface, even the cold surface of a rogue. The convection in the mantle weakens, the volcanic activity that had been shaping the interior quiets. The core cools toward solidification. The magnetic field, if there was one, weakens and fades. Whatever chemistry had been operating in any subsurface liquid layer depends on the heat from below, and as that heat declines, the liquid layer slowly refreezes from the bottom up until the world is cold throughout. A solid body with no liquid interior and no magnetic protection and no source of warmth except the faint uniform background of the cosmos. That end is not violent. There is no explosion, no collapse. The cooling is slow enough that nothing dramatic marks its progress. The surface, already frozen to within a fraction of absolute zero, barely changes. The change is interior, invisible, measurable only in the decline of the world's magnetic field and the stilling of its mantle. The end arrives not as an event, but as the absence of a process. The way silence arrives, not as a sound, but as the ending of one. The world continues to move. It will always move, unless something stops it. But it moves as a cold, still, solid thing, carrying no more warmth than the space around it, indistinguishable from the void it moves through, except by its mass and composition. That is the longest future most rogue planets face. Not capture by a star, not encounter with another body, just the slow convergence toward thermal equilibrium with an interstellar medium that is already nearly as cold as temperature can be. A process that ends not with arrival, but with a kind of completion, a world that has given everything it had to give, and now drifts as peacefully as anything in the universe drifts, spending no energy, losing no heat, changed by nothing and changing nothing, a planetary mass moving at a constant velocity through the dark for as long as the dark continues. The dark continues for a very long time. The stars have perhaps 10 billion years left to form, on average, before the available gas in the galaxy is consumed. After that, the existing stars will burn through their remaining lifetimes, one by one, the longest lived lasting trillions of years past the era of star formation. The rogue planets will outlast most of them. A cold, solid rogue planet, no fusion to exhaust, no instability to trigger, persists indefinitely in the absence of a direct encounter with something massive enough to disrupt it. The galaxy will have changed beyond recognition before the rogue planets that formed in the early universe have come to the end of anything. They may be among the last objects in the galaxy that retain the composition and structure of a world, long after the stars that made them have cooled to black dwarfs, and the space between everything has grown wider with the slow expansion of the universe. In that very long future, they still move, still planetary, still carrying in their rock and ice the chemical record of the molecular cloud that made them, the heat signature of the radioactive isotopes that warmed them, the orbital history written in their velocity and direction. No one will read that record. There will be no one to read it, but it will be there in the way that information is always there in the arrangement of matter, regardless of whether any mind is present to interpret it. Somewhere in the outer Milky Way, at this moment, one such world is moving, not toward anything in particular, not away from anything. Its surface is cold, colder than any environment that has a name in ordinary life, cold enough that the atmospheric gases of familiar worlds would solidify and fall as frost. Its interior, still faintly warm, convects in slow and patient patterns that have been running since before any living thing on any world thought to look at the sky. Its magnetic field extends in an invisible sphere around it, deflecting the sparse radiation of the interstellar medium, protecting the darkness within from the radiation of the darkness without. No sun rises on its horizon. No sun has risen there in a very long time, if one ever did. The horizon itself is dark, a clean, sharp line between the frozen surface and the field of stars too distant to provide any warmth, each one a point of light, no brighter than any of the others, forming no particular pattern, casting no shadow, illuminating nothing,